Okay, let's go ahead and look at our notes. I know we started the notes and then all of a sudden we had this madness happen again, and now we're back at home for a little bit. So we're still going to go ahead and do the notes in class, but I thought let me go ahead and just record them too and post that, and maybe that might be, easier for some of us to look at the notes that way. But if not, like I said, we're still going to go over the notes in class to make sure that we understand when we're talking about bonding and naming. So please, if you haven't had a chance, go back and re-look at the calendar. It had to change again. Again, if for some reason we should be going back to class, but again, later on in the school year, if we get sent home again or something happens, please know that our calendar may have to revise and change again, okay? So it's just an ongoing process, right? Until we can get settled back into going traditionally to school. But let's go ahead and take a look, just as a reminder and review. Let's look at what we talked about already. We talked about first thing is here, it says up here is, why do atoms bond? Well, they bond because they want to become stable. Now, for them to be stable, they have to follow what we call the octet rule, which is 8 valence electrons in their outermost shell and keep that full. There's an exception to the rule, which is hydrogen and helium, who they need 2, forgive me, 2, they need 2. Now, atoms are going to do anything, so that way they can get to this octet rule. They're going to share, they're going to gain, and they're going to lose. Okay? Now, let's talk about what we call ionic bonding, and then we're going to talk about what we call covalent bonding. Those are the two main types of bonding that occurs, ionic and covalent. Now, ionic bonding occurs between a metal and a nonmetal. One more time, between a metal and a nonmetal, or we can say a cation and an anion, or a positive ion and a negative ion, right? Now, when we're doing this and we are bonding them together, I don't recall where I didn't say it in our class notes, so let me say it here. I'm trying to look to see if I have a highlighter. Here's a yellow marker. But this is really important when it comes to ionic bonding. So I'm going to go ahead and make a little box here. That when we're bonding, the metals go first. Now, it's a metal and a non-metal. Remember, I told you how I memorize it. I memorize it as it's ironic when two things that are opposite come together. Ionic is when two things that are opposite, metal and non-metal, bond together. Now, when they bond, though, the metals go first. The metals are going to be bonded first. So when they come together, the metals will be named first. They're going to go first in order. Okay? Then we talked about, well, let's just look at fluorine and calcium. Okay, traditionally, it's so easy when we have somebody in group 1 and group 7 that bond together, because all you need is one of each, but it doesn't always happen like that. So when we do this bonding, the visual long method, so that way you can visually see it, would to be go ahead and write out the symbol for that element and then draw out the dots, which what we call the Lewis dot structure, on the outside. Remember, this Lewis dot is the outside valence electrons, which is the same thing as a group number. Now, when we do that, we can see that calcium has 2 here. And what's calcium going to do? Calcium's going to get rid of them. And fluorine so happens to need 1 each. So one's going to go here and one's going to go here. And that's how they're going to bond. When calcium and fluorine bond together, we're going to have 1 calcium is needed and 2 fluorines are going to be needed. Okay? And we can see that calcium becomes a +2 oxidation number and fluorine has a -1 oxidation number. Then we practice again. Then we come over here to what we call the crisscross method. And the crisscross method is pretty much what most people do. But not only that, but you can always math justification. You can go ahead and prove that this is correct when you do the crisscross method. Okay, what happens in the crisscross method is that you're going to go ahead and get the ionization number. The oxidation number is what I meant to say. You're going to write it at the top. Where did I get the oxidation number? I had to go to the group number and look at it to see how many valence electrons there are. So now I get that oxidation number and I cross them over. And this is just a shortcut method. This tells me that calcium is going to have 1, even though there's not a number here, it's invisible. 1 calcium and 2 fluorine are going to be bonded together when we crisscross those oxidation numbers down. Same thing over here, sodium, Na, and sulfur. Well, sulfur has a -2 charge, and Na has a +1 charge. When I crisscross them, ignore the plus and negatives. And so when we crisscross them, Na is going to need 2 of them, and sodium is only going to need 1 to bond, okay? There are 2 here for you to practice, and then you need to finish down here as well. Let's turn the page because we did all of this in class already. Then we get to this side over here and we talk a little bit about transition metals because they're also metals, and we talk about this other thing that we call polyatomic ions. Okay, a polyatomic, because the word poly means more than one, is going to be an ion that's going to bond, right, with it's going to bond with another one non-metal. Most of them are non-metals and non-metals. So polyatomic is, carbon and oxygen. They're bonded together, and they're stuck together. They come in a group. They're not going to leave. They're always going to be stuck together. And so we call them polyatomics. They don't have to be memorized. We are going to have a chart for that. So back to the transition metals. Transition metals are special. Don't forget lead and SN10. They are not in the little square, but they are also included into the transition metals. They're different because they have more than one charge, okay? +1, +2, +3, or +4 charge, just depending. Why is it a plus? Because remember, all metals become cations, which is a positive charge. And so we're going to come over here and we're going to see, when we see the Roman numerals in the parentheses, that's actually the oxidation number, the charge number. So we're going to go ahead and put that Roman numeral 1. It's going to be up here, +1. Sulfur is a -2 charge. Crisscross them, and then bam, we're done. But we cannot forget that we still need to reduce. So when it comes to ionic bonding, we need to reduce them, okay? And 2 and 2 could be reduced to 1 and 1. Okay. Again, sometimes for nonmetals, it may not just be a traditional nonmetal. It might be what we call a polyatomic, right? Again, they come together as a group. We ended up here when we were practicing. All right, we practiced 4 of them over here, and then we stopped here. So let's look at this. What about 2 polyatomics bonding together? Well, let's look at that. Write the formula for a compound containing ammonium sulfate. Ammonium and sulfate. All right, so let's come over here and let's find ammonium. Ammonium is going to be, let's see. Here it is, a +1 charge. So I'm just going to put a +1. Sulfate, right here, ATE is, and we look up here, a -2 charge. So this tells me here that we're going to, because we know we're going to crisscross, right? And so we can go ahead and crisscross them. And let's write ammonium down. Ammonium is over here, NH4. And what's going to happen? We have to put a parenthesis if we're going to have a number behind it. So when this 2 crosses over, we can't put a 2 right here by the 4. So we're going to have to put parentheses with the 2. Sulfate. Sulfate is over here. Sulfate is going to be a SO4. This little 2 is the same thing as just the -2 charge. So when it crosses over, it's going to be a 1. No parentheses there. Leave it like that. And that's what it's going to look like. Okay? It looks like that. That's my answer. So yes, it's possible to have polyatomics bond with each other. Let's keep going. Let's talk about the next type of bonding, which is a pretty crucial, important one, popular one here. We call covalent bonding. Covalent bonding says here chemical bonds resulting from the sharing of valence electrons. Most covalent bonds are between two nonmetals. Exceptions, B, E, and B. Okay, remember, we're going to have so many exceptions coming up. It says here that the shared electrons are considered part of the complete outer energy levels of two atoms. Bonding pairs or shared pairs, it says here, paired of shared electrons between two atoms. Okay, and it's gonna make a little bit more sense in a little bit. Lone pairs are unshared paired of electrons. And we've got, remember we talked about this like in the beginning, it might have been unit 1 or unit 2, diatomic molecules. And we had to memorize those. H2, N2, F2, Cl2, Br2, I2, and O2. Do we just memorize them? No. We use them, remember what we call the 777 rule? Okay, but if you look at this diatomic, Di, what does the letters Di mean? Di, what does di mean? Di means two. Okay, which diatomic molecules always comes in twos. They come together, okay? They come paired together always. Alrighty? So we will definitely look at them as well, but we use what we call the 777 rule, where they start at atomic number 7, which is nitrogen. They make a number 7 on the periodic table, and there are 7 of them total. Do not forget hydrogen, who's way over there by himself. Okay, he's like out of the loop of this. He's not part of it, but he still is. So let's go ahead and let's look at this and see what this is going to start to mean a little bit over here. Types of covalent bonding. Well, when they share these electrons, we end up with single covalent bond that can occur when two atoms share one pair of electrons. For an example, hydrogen, which is a diatomic, we have, let's go ahead and draw the Lewis dot structure. We're going to have a hydrogen atom here, a hydrogen atom here. He's going to have one valence electron. What's going to happen is that they're going to bond here. And when they do, they're going to have a hydrogen, hydrogen. This is what it looks like when the bonding occurs. Okay? This one line represents 2 electrons. One more time, one line represents 2 electrons. Why? Because there's 1 electron here and 1 electron here. 2 electrons is going to make him happy, and he's going to be content with his octet rule. Okay? Multiple bonds, double covalent bonding, is when 2 atoms share 2 pairs of electrons. So for an example, oxygen, okay, O2, which is also a diatomic. Let's go ahead and let's do the Lewis dot structure. Oxygen here, oxygen over here. And I know I'm not gonna draw it correctly. That's because I want my bonding to occur. 1, 2, 3, 4, 5, 6. Oxygen's in group 6. 1, 2, 3, 4, 5, 6. Now, he needs an extra one over here, and they need an extra one over here. So there's two spots for electrons to come. They need 2 electrons. Well, they need an electron here and they need an electron here. So what they're going to do is they're going to bond here and they're going to bond here. And when they do that, it becomes, or it looks like this. Oxygen, oxygen. How many shared electrons? 2 pairs. 1, 2. Right? How many electrons does each line represent? It represents 2. So this represents 2, 4, 5, 6, 7, 8. Let's look at this oxygen. This one's considered 2. That one's 4, 5, 6, 7, 8. So now each of them are full. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, and they are sharing them, and they are happy. Triple covalent bond is when two atoms share, exactly like you're thinking, 3 pairs of electrons, right? Now, nitrogen, or N2, which is also a diatomic. Let's look at that. N and N. Go to the periodic table so you can find out that nitrogen is into group 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And what's going to happen is, yes, they're going to share here, they're going to share here, and they're going to share here. And so now when they bond together, when we draw it out, it's going to look like this. 1, 2, 3, right? A triple bond. Each line represents two valence electrons. How many do they have to have? They have to have 8. So let's just look at this nitrogen already. Just this one. 2, 4, 6. All he needs is 7, 8, which are those two right here. Let's look at this one. 2, 4, 6, 7, 8. Okay? Again, practice over and over and over is what we're going to need for some of this. Now, when we look at those single, double, and triple bonds, the single bond, actually the length between those two hydrogens should be, and I know you can't see it in my drawing because I didn't represent it that way, but the bond length is the longest length. The double is shorter, or I'm going to put right here shorter than the longest one, and then this is the shortest. They're closest together. So the nitrogen triple bond is really a tight bond and they're close together. Now the single bond is really the weakest. Imagine between the two hydrogens, they just have one string holding them together. All right. The oxygen has 2 strings. They're holding on to 2 strings, and the nitrogen's wrapped up or tied up with 3 strings. So that's going to be the strongest bond strength. And then bond dissociation energy, sorry. Okay, what does this mean? This means how easily it breaks. And this is going to be the lowest. This is going to be higher. Oops, can't even spell. And this is the highest. Okay. So let's keep going in our notes. And identifying the correct drawing for molecular compounds. So we're going to do some what we call molecular drawing. Okay, what it looks like when they're bonded together. So there's a few steps here. Again, they may not make sense at first. We're going to have to practice this first for a little while before it starts to make sense. Number 1, add up the total number of valence electrons available for each atom in the molecule that we're bonding together. Number 2, make sure that the outer atoms are symmetrical arranged around what we call the central atom. Shortcut for central atom is the Ca. Okay? Which I guess goes there. I was jumping the gun over there. Okay, the central atom will have the most bonds. Usually, it's going to be located leftmost on the periodic table. So remember when it came to the ionic bonding, when we had metals and nonmetals, and I told you that the metals always come first? Okay, Those were pretty easy. When we're talking about bonding here and we want to find out who the central atom is, the central atom is probably going to be the atom that's most left on the periodic table. Okay? Carbon is guaranteed always a central atom. And hydrogen is always what we call the terminal atoms, or the outside. See, those are terminal, and that's central. That's central, those are terminal. Okay? Next one, number 3. Count the total number of electrons in the compound and make sure that it equals the total that you counted. Okay, don't forget though that when we're counting them, lines, that a line or that a bond is lines equal a bond that is 2 electrons. Dots are electrons, or dots equal electrons that are only 1 electron each. Right? Remember how we talked about the single, double, and triple bond? Right? So when it had the hydrogen and it had the single bond, that one line equaled 2 electrons for that atom. Okay? Next one. Number 4. Make sure each element has a full valence shell. Right? Hydrogen needs 2 and boron needs 6. And this is an exception to the rule. Every other element on that periodic table needs to have 8. Okay? So it says here, let's go ahead and look at some examples of what is good and what is not. And we will go through practicing this together. We're going to look at A, B, C, D, and E. And between them, we're going to look at letter A, and we're going to look at all of them. And only one of them is correct. Okay? And we're going to keep on going that way. So let's see, and let me show you how I bond when it comes to this and how I add them up and count up those valence electrons and stuff, okay? First thing here is that I have Si and I have F4. Okay, so Si and F4. Well, first thing is there's only one Si and there's 4 fluorines, right? So I'm going to come over here and just write down a little bit of stuff so that way I know what I can maybe roll out some easy stuff. So Si equals 1 and fluorines should be 4. If that makes sense, because I look at the bonding here. And look at this one right here. There's 1, 2, 3 fluorines. It absolutely cannot be this one. Make sense? Cannot. Why? I'm going to go ahead and put it over here. Because we need 4 fluorines, not 3. Let's look at this one over here. Next one. Can it be this one? Cannot be this one. Why not? Because we need 4 fluorines. There's only 3. So now 1 Si, 4 fluorines, 1 Si, and 4 fluorines. Okay, looks good. Now, when we do our drawings, we need to account for every valence electron. Not every electron, every valence electron. Okay? Remember, the valence ones are the important ones because they're the ones that do the bonding. Okay? So they need to be accounted for, or they need to be seen, if that makes sense. Okay? I need to be able to see them and be able to count them. Now, in this case, let's go ahead and let's come over here and we're going to do what we call counting. Okay, we're going to count them up. We're going to do where it says right here, we're going to add up the total number of valence electrons available for each atom in the molecule. So how many valence electrons does silicon have and how many valence electrons does fluorine have? In this case, you probably should go grab that periodic table. So when you grab the periodic table so you can look at it, let me go grab my periodic table too. And I thought I had one closer to me. I guess not. All right, well, this is the only one I can find right now, so let's use this one. Silicon. Let's go find silicon. Silicon's a nonmetal. It has 4 valence electrons because it's in group 4. So I'm going to come over here and I'm going to put 4. Now, how many fluorines do we have? We actually have 4 fluorines. So I'm going to go ahead and put F here, and F here, and an F here, because there's a total of 4. Let's look. Fluorine is in group 7. So there's 7 valence electrons. 7, 7, 7, 7. We need to add them all up, so that way we can figure out how many valence electrons total do I have in this bond. So 5, 10, 15, 20, 2, 4, 6, 8, 28, 29, 30, 31, 32. So there's 32 valence electrons total when this bonding is going to occur between 1 silicon atom and 4 fluorine atoms. So I just want to write valence electrons, 32. So when I'm doing this, remember, we've got to find one that's going to be what we call the central atom. Well, they obviously found it for us already. It's silicon. But let's look at, remember the rules? It says here that it should be the one all the way to the left, or the leftmost on the periodic table. Here's fluorine, here's silicon. Silicon is closer to the left than fluorine, so obviously that is correct. All right? Now, remember, each line represents 2 electrons. So 2, 4, 6, 8. So I'm just going to put right here 2, 4, 6, 8. Right? Or 2, 2, 2, and 2, which totals 8. This shows me that there's only 8 electrons. And there should be 32 valence electrons total between all 5 of those elements or atoms bonding together. Let's look at this one. 2, 2, 2, 2. That's 8. So 32 take away 8, right, is where we're at right now. So we're at 24 valence electrons left that we must use. And if I come back over here, this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Take away 24 equals 0 left over. This is the correct one. This is incorrect. Why is this one incorrect? Only has 8 electrons. It needs, or I'm going to put 8 valence electrons. It needs 32 valence electrons. Okay? So that's the reason why this one's not going to work and this is correct. And again, I know this is like a lot I'm throwing at you right now and we're not in class, but that's what the rule is trying to tell us here, is how to do it with our math. Count them all up. You're able to see one more time, every valence electrons for all of those atoms need to be shown. Okay? That's what our molecular drawings are going to show us. Okay? Let's practice this again, because I think it's going to take us a little bit of practice before we, get better at this. Letter B. Letter B is going to ask you, between those 4, which one is the correct way to bond CO2? Now let's look at this. I'm going to come over here, and I have 1 C and 2 oxygens. So I'm going to come over right here. I'm going to put COO, because that's what this bond is occurring. 1 carbon and 2 oxygens, a total of 3 atoms. What do I need to do? First step is I need to come over here and let's look. 2 oxygens, 1 carbon. 2 oxygens, 1 carbon. 2 oxygens, 1 carbon, 2 oxygens, 1 carbon. So, okay, they all at least have the minimum amount or the correct amount of atoms needed. Now, let's come to our periodic table, look at the group number, so that way we can write down the number of valence electrons. Carbon's in group 14, so there's 4 valence electrons here. Oxygen is over here in group 16, so this one has 6 and this one has 6. We add them all up, 5, 10, 15, 16. So that's 16 total valence electrons between all 3 of them bonded together. We have to use up all 16, and all 16 need to be shown. Okay, so let's look just to make sure that something's not obviously incorrect. Okay, now I see 2, 4, 6, 8, 10, 12, 13, 14, 15, 16. Let's keep going. 2, 4, 6, 8, 10, 12, 14, 16. Okay. 2, 4, 6, 8, 10, 12, 14, 16, 17, 18, 19, 20. Whoa, wait a minute. Definitely not you. Why not? Because there's too many valence electrons. We need to have 16, not 20, not 24. Let's look at this one. 2, 4, 6, 8, 10, 12, 14. Nope. Not enough valence electrons, right? We got to have 16, not 14. So now we're at least between those two right here. Hopefully this is going to help you at least to knock down your choices. So we started off at 4, now we're at 2. So when we look at this, we've got to decide. Now, the next thing is also, we want to make sure that we're symmetrically arranged. Believe it or not, the more symmetrical we are, the easier it is and the less energy it takes. Okay, that's first. And both of them are symmetrical. Okay, well, I see that. That seems like that's good too. The other thing is between the carbon and the oxygen, carbon is more to the left, and there's always a guarantee that if we have a carbon in our bond, in our atoms that are bonding, it's going to guarantee be this what we call central atom. So those two are also going to be good there. So we can't complain about that either. Let's go ahead and let's look. Carbon. This one is 2 electrons here. That line means 2. And this line means 2. So how many valence electrons does carbon have in that case? 2 here means 4. How many valence electrons does carbon have to have? Carbon has to have 8 valence electrons. Remember, there's a few exceptions to the rules. Hydrogen and boron. Other than that, every other element on the periodic table needs to have 8 valence electrons. Okay? Everybody has to have 8. So since carbon only has 4, that's not going to work. Let's look at oxygen though too while we're looking at this. 2, 4, 6, 8. 2, 4, 6, 8. So it looks like the oxygen is nice and happy, but the carbon is not happy. So carbon only has 4 valence electrons and needs 8 valence electrons. Let's go ahead and double check to make sure this is correct too though. I don't want them to mess us up. Carbon, 2 here, 2 here, 2 here, 2 here. 2, 4, 6, 8. Ooh, let's look at oxygen. Cover that up so that way you can just look at the oxygen. 2 here, 2 here, 2, 4, 6, 8. Let's look at this oxygen. Cover that up. 2, 4, 6, 8. This is our correct answer. Everybody's happy.